Good afternoon, everyone. My name is Julie de Kock, and I'm a scientist at the Qatar Biomedical Research Institute, and I will be your moderator of today's seminar. Today, our seminar is focused on COVID-19 outbreak prediction and assessment of prevention policies, a data science approach. It is my pleasure to inform you that we actually have two speakers today. So today we have Dr. Abdelkarim Eradi with us, as well as Dr. Ahmed Ben Said. Dr. Abdelkarim and Dr. Ahmed received a rapid response call grant from QNRF to conduct the work that they will be sharing with you today. As you might already know, that it is very important to have accurate forecasting of COVID-19 propagation to assist policymakers in taking adequate decisions to stop the spread of the pandemic. In this webinar, both Dr. Abdelkarim and Dr. Ahmed will share with you some information on two COVID-19 deep learning prediction models that they have developed. The first model uses a deep learning approach to forecast the cumulative number of COVID-19 cases based on data from countries that have similar demographic, socioeconomic, and health sector indicators. The model also takes as input the adopted lockdown measures. And in the second approach, again, the model uses a deep learning approach for evaluating and predicting the impact of various lockdown policies on daily COVID-19 cases. Quantitative evaluation of their proposed techniques show that they can improve forecast accuracy of the daily cumulative COVID-19 cases. And in addition, because they have used Qatar as an example, also highlights that lifting restrictions, particularly in schools and border opening, would result in significant increase in the number of cases during the study period. So, as I mentioned, today we have two guest speakers. Our first guest speaker is Dr. Abdelkarim Eradi. He is an associate professor in the Computer Science and Engineering Department at Qatar University. His research and development activities and interests focus on service-oriented computing, cloud service composition, and mobile crowd sensing. He leads several funded research projects in these areas, and he has authored several scientific papers in international conferences and journals. Dr. Abdelkarim received his PhD in computer science from the University of New South Wales in Sydney, Australia. Besides his academic experience, he has 12 years of professional experience as a designer and a developer of large-scale enterprise systems. Our second speaker will be Dr. Ahmed Ben Said. Dr. Ahmed received the PhD degree in computer science from the University of Burgundy, France in 2015. He was a research assistant with Qatar University on several projects, including the simulation of surgical cutting operation using 3D modeling, the usage of multispectral image for face recognition, and the development of a reliable mHealth system for remote patient diagnosis. His research interests include machine learning and computer vision, and he is also interested in urban computing and mobile health systems. Dr. Ahmed is currently a senior student success specialist at the Student Experience Department at Qatar University. Before I hand over to Dr. Abdelkarim to share his slides, I first want to share some housekeeping rules with everyone, all our attendees. So first of all, the microphones of all attendees have been silenced. They have been muted, so you cannot speak up. However, we strongly encourage you to submit any questions through the Q&A tab and address them to all panelists. So please don't use the chat, but use the Q&A tab. After the presentation, we will have a joint Q&A session. So we will then combine all the questions, whether it is related to the presentation done by Dr. Abdelkarim or Dr. Ahmed. So without any further ado, I would like to invite Dr. Abdelkarim to start sharing his presentation, please. Thank you. Dr. Abdelkarim, you're muted. Can you try again?
I think you can hear me now.
Yes, now it's working. Great, thank you.
Excellent. Okay, thank you very much for the nice introduction. So this presentation is intended to share with you some of the work we have done during the summer as part of the QNRF-funded project. Was part of this RPC call. I think they called it a rapid response for COVID-19. And it was funded for 3 months, and myself, Dr. Ahmed, and 2 students, Hussein and Abdul Mun'im, worked on this project from June to August. And the aim was to apply machine learning techniques, especially deep learning, to enable us to predict future cases and also to assess the effectiveness of prevention and lockdown policies. So in this presentation, what we want to, the presentation outline will be like this. First, I will introduce the motivation and the objectives of this project. And then Dr. Ahmed will present the details of the forecasting models that we have developed. And also he will highlight, we basically built 2 models. One considers the socio-demographics and health indicators, and as well as the lockdown measures to predict the future cases. So we built 2 models that he will present. Then these models, we've used them to allow end users to do predictions for future cases on a web-based interactive dashboard. So the aim, as I explained, as I mentioned before, the aim was to use the power of data science and the latest advancements in analytics to try to better understand the COVID-19 outbreak, and also try to analyze the effectiveness of the lockdown measures that governments around the world have adopted. So what is really different in our prediction model is that we not only consider the daily cases that are collected by many organizations, but also we try to factor other indicators, such as the social demographic indicators, including the percentage of age groups, the country GDP, the environmental and pollution levels. We also considered some health indicators, such as the percentage of smokers, the numbers of ICU units, the number of doctors per 1,000 population. Additionally, we considered the lockdown measures that were taken, such as the closing of schools, closing workplaces, closing of transport system, and also restrictions on gathering. So we took all these indicators and feed them to this, we use them to train a prediction model, and with the hope, the ultimate goal is to enhance the accuracy of the prediction. And then the second step of the project was to try to evaluate some scenarios related to easing the lockdown measures. If we let's say lift some restrictions on the workplace or some restrictions on the gathering, we want to see what is the impact of such easing of restrictions on the predicted cases. So those are our goals. So the core of the system is the prediction models that we have built, and then we use them to drive an interactive dashboard. So this dashboard is very similar to many dashboards out there that are providing daily statistics about the COVID-19 data. But what is different there, what is different in our dashboard is the ability to do these predictions and the ability to do this what if scenarios, what will be the impact on the predicted cases if the government decide to change the lockdown measures. So now I'll hand over to Dr. Ahmed. He will present the details of how the the prediction models were trained, and also the results, the evaluation results of the evaluation results of the models that were trained, and then I will come back and discuss the how we use the trained models to drive the dashboard.
Thank you, Dr. Abdelkarim, and thank you for the panelists. So let me start by sharing my presentation. Okay, so as Dr. Abdelkarim said, we had actually two main research themes and one practical theme. And the research theme, we had two aims. The first one is to come up with a model as accurate as possible that enables the forecast of the daily cumulative cases of COVID-19 during the study period. And we used Qatar as a use case. So, and then in the second research theme, our aim is essentially to test some scenarios, some hypothetical scenarios, in the hope that it will enable decision makers to take the appropriate lockdown policy at the appropriate time. So, starting first with the details of the first research contribution, which is the prediction of the daily cumulative cases of COVID-19. So we have done some literature review, and we found that most of the contributions were that addressed the problem of forecasting of COVID-19 relies on some historical data of a specific country in order to predict the future. So we said, in order to achieve better performance, we need to think differently. So instead of relying on data from each country individually, we said, let's now group countries that have some specific, that share some specific properties, and in addition, include some additional information, which is basically the lockdown measure. And it's widely known that lockdown measures usually impacted or affected the growth of COVID-19 cases around the world. So first, we started by collecting some specific data. This specific data describes the demographic and socio-economic situation or characteristic of the countries around the world, in addition to some health indicator. For example, we calculated the average population of age groups. For example, the percentage of people between 0 and 4 years old, 5 to 9 years old, 10 to 14 years old, etc. Percentage of smokers, the GDP of the countries, and the density of the population. In addition to the percentage of smokers, the number of ICU units, the number of doctors per thousand population, and also the average and the monthly average number of tourists during the last 5 years. So all this data, we will take all this data, apply a cluster analysis in order to group countries sharing these similar properties. And once we were able to cluster these countries, we will zoom into a specific cluster. If we will study, for example, Qatar as a use case, we will zoom into the cluster where Qatar is located. So the cluster in which Qatar belongs. And we will collect the data of the countries, not only for Qatar, but for countries who are members of the same clusters as Qatar. So given all these countries, members of the same cluster, we will collect, in addition, the daily COVID-19 cumulative cases of these countries, in addition to information about the lockdown measures. So we addressed five lockdown policies related to school or educational institution, workplace closing, border closing, the gathering, restriction on gathering, and public transports. So we addressed 5 lockdown policies. So with to achieve the cluster, to perform a cluster analysis, we intended to apply the well-known k-means algorithm. However, k-means require a specific input, which is the number of clusters. So in order to, given a data, in order to discover or to find the highly likely number of clusters, there are certain methods that we can apply. Among them, and the most well-known method is the elbow method. And I recall from our experiments, the number of clusters we obtained is around 40. Given all the data for almost all countries around the world, we collected their data, we applied the elbow method. The number of clusters was around 40, followed by k-means, and all the details of this framework. So a glimpse of the lockdown measures data. So for example, for school, a level of 0 or a value of 0 in our data means that all educational institutions are open. There is no restriction at all. A value of 1 or level 1 means that the authority recommends closing all educational institutions. A value of 2 means that all education or certain educational institutions are required to close. For example, close all universities and keep high school opens. A level of 3, which is the most strict one, let's close all educational institutions. For example, let's take, for example, public transport. For public transport, a level 0 means there is no measure at all. A level 1 means that the authority recommends closing or reduce the volume of the traffic, closing some routes, or means shutting down some means of transportation. Level 2, which is again the strictest level, require closing all public transport services, no restriction, no exception at all. In addition to also the restriction on gathering, on workplace, and on borders. So for example, for borders, a level of 0 means there are no restriction, and a level of 4 means ban all arrivals from all regions around the world. So these are certain levels related to these lockdown policies. So our study period for this framework is from 14th of, we took the data starting from 1st or I think 14th of February up to 31st of July. So we apply our cluster analysis, and surprise, surprise, Qatar, Bahrain, Oman, and UAE fall in the same cluster. It turns out they share similar demographic, socioeconomic properties, and in addition to some health sectors indicators. So here we emphasize that we did not include any geographical information in our data in which we applied cluster analysis. So by July 31st, Qatar had more than 100,000 cases. Oman had around 80,000 cases. United Arab Emirates had around 60,000 cases, cumulative cases. Here we are talking about cumulative cases. And Bahrain had around 40,000 cases. So now we collected the data of cumulative cases of all these countries, in addition to their lockdown information or lockdown data. We will use it to train a forecasting model. So our choice of forecasting model is the bidirectional LSTM. So bidirectional LSTM is a specific type of deep neural network, which is derived from another specific type of deep neural network, which is LSTM, or long short-term memory. So an LSTM layer has some LSTM cells, and inside an LSTM cell, and by the way, LSTM is most suited for sequential data, such as time series, speech, or text. So there is like sequential property in the data. So inside an LSTM cell, all this transformation on the data will occur. So inside an LSTM cell, so given the input from the previous LSTM cell and the value, the current value, there will be all this transformation inside the LSTM cell, and we will have 3 outputs that will be linked to the next LSTM cells. So what is it about bidirectional LSTM? So bidirectional LSTM takes LSTM to another level. So if you noticed in LSTM, the data is fed sequentially in forward way. So xt minus 1, then xt, then xt plus 1. So this is the forward path. Not only the forward path, in bidirectional LSTM, we feed the data in backward way. So we start by xt plus 1, xt, then xt minus 1. That is, we are not only training the model on the past to predict the future, but also on the future to predict the past. And surprisingly, this strategy has led to significant performance improvement compared to LSTM in several research problems, specifically related to time series. So in our evaluation, we wanted to prove or validate two things. First, the importance of including lockdown measure in the training data, and also training the model on several countries at the same time, and also compare the model with certain state-of-art prediction model. So in figure 5, we trained 6 models, bidirectional LSTM with lockdown information, and trained on countries from several countries. Also LSTM, same thing. Bidirectional LSTM now with lockdown information, but only trained on data of Qatar. And also bidirectional LSTM without any lockdown information, and same thing for LSTM. And our quantitative evaluation showed that indeed, including both the lockdown information and training the model on data from several countries has led to significant improvement. In the second evaluation, in the second assessment, we compared our model against certain state-of-art prediction approaches suited for time series, such as the ARIMA model, the autoregressive integrated moving average, the simple moving average with 6 days lag. So we found out that 6 days for simple moving average leads to the best performance compared to other lag days. In addition to the double exponential moving average. And it turns out that indeed our model led to a great and a significant performance improvement compared to all these models. So now we move to the second research theme, which is assessing or providing a way to conduct a what-if analysis related to lockdown policies. And here we have adopted almost the same framework, but with some change into the data that we have used to cluster. So we said now we will cluster the data based on 2 main characteristics. First, we will group countries who are, in terms of how fast they reacted to the outbreak of the virus, and also how efficient their lockdown policies was. So for the first one, how fast? So we calculate the difference in days between the day the first case has been reported and the day each lockdown measure has been imposed. Let's say, for example, in Qatar, the first case was reported on 14th of February, for example. And schools were shut down, all the educational institutions were shut down on 15th of March. So roughly we have around 1 month in difference. We did this for all the 5 lockdown policies: the educational institution, the workplace, the borders, the public transport, and the restriction on gathering. Same thing, we apply the elbow method to determine the optimal number of clusters. K means to cluster the data. Then we zoom in into the cluster where Qatar is located. And now we train a model on the daily COVID-19 cases of all these countries, member of the same clusters, in addition to lockdown information. So once we obtained and we made sure that our model is very performant and leads to a minimal error between the actual and predicted values, we can establish some scenarios, some hypothetical scenarios. And here our study period is from 1st of September to 7th of September. And we know that Qatar moved to the 4th level of lockdown on 1st of September. So how to test or how to establish a what-if analysis? So let's say that we want to test the scenario where all schools are open. Students and all students are back to schools starting from 1st of September, while keeping all restriction as it is in reality during the study period. What would our model predict in this period of analysis? So first, Qatar was in our cluster analysis. Qatar, I forget to note that in terms of efficiency, so we said that we have how fast and how efficient. In terms of efficient, so we calculated the well-known RT or R0 score. So R0 is basically, I can say the headache or the basically the headache for all health authorities around the world. They are trying as much as possible to reduce this number below 1. So a value of R0 below 1 means that the virus is being contained. A value greater than 1 means that the virus is propagated in the country. So given all the countries we have, we calculate the value of R0 on daily basis, okay? And then we average the value per 15 days. So each 15 days, we take the daily values and we average them. So we did this for the study period from 15th of March during up to 7th of September. So our cluster analysis shows that Qatar falls in the same cluster as all these countries, including Azerbaijan, Benin, Georgia, Croatia, Kuwait, Italy, Norway, Oman, Pakistan, Romania, Seychelles, Lebanon, and Mexico. So several countries. So our cluster analysis says that in terms of efficiency and how fast they reacted to the outbreak of COVID-19, all these countries have roughly the same response. So moving now to the hypothetical scenarios, which has been tested in the period from 1st to 7th of September. So we will study each lockdown policy separately, while fixing all other lockdown policies as it is in reality during that period. So starting by school and educational institution. So what happens if all schools are open or educational institutions are open, no restriction at all, while keeping all restrictions as it is in reality? Again, this is for Qatar. So we noticed that during the first 3 days, from 1st to 3rd of September, the model predicted almost similar to the actual values we obtained during that period. So the model output fluctuates around the actual values. However, starting from the 4th day up to the 7th day, we can clearly notice an alarming increase or a continuous increase of number of cases up to the 7th of September. Again, this is limited to the study period. So now what happened if Qatar fully opened all public transport? No restriction, while keeping all restrictions as it is in reality during the study period. So our model did not detect we cannot notice any alarming pattern. So the output of the model kind of fluctuating around the actual values. So no alarming pattern. Now, restriction on gathering. There is no restriction on gathering during that period. Again, the model did not show any alarming pattern. The numbers fluctuate, or the model output fluctuate around the actual values. Similar to restriction on workplace, no restriction on workplace, while keeping, again, all other restrictions as it is in reality. So there is no alarming findings. Now, if Qatar fully opened the borders, there is no restriction at all, okay? And while keeping, again, all restriction as it is. So again, the model output during the first 3 days fluctuates around kind of the actual values. However, starting from the 4th day, the model forecasts an exponential growth in number of cases, which is kind of very alarming during, again, that period. So to summarize, our model is telling us that if Qatar, during that period, open school, no restriction, or fully open the border, there will be indeed a significant increase of daily COVID-19 cases. For other restrictions on public transport, on gathering and on public transport and workplace, there is no significant increase or alarming increase in terms of the daily COVID-19 cases. So that's it with our research findings. And now we move to the practical outcome of our research, which is the development of an interactive dashboard where we put all our findings available to the public. And now I will pass to Dr. Abdelkrim to present this part. Thank you.
Okay, thank you very much, Ahmed. Yes, let me just. So basically, so what we did, because part of the outcomes of this project, like the funding institution, they really require something practical, not just the models that we have built. So we put this together in an interactive web dashboard that is available on this link. This is hosted on a free server for now. We're trying to move it to maybe QU server. We're negotiating the ability to do so. Especially, it needs to be publicly accessible, and there are some security concerns. So we are addressing those, and hopefully we put it on a more stable server. And now also the source code of the dashboard, as well as the model, as well as the data that was used for building the prediction models, are all available open source on this GitHub link. So those of you interested to explore further. So the dashboard is similar to many other dashboards that we're all familiar with. So it gives the number of confirmed cases, the recovered cases, the number of deaths, the mortality rates, the strictness index, the total tests. So all of this is normal, nothing novel here. All dashboards are providing all this information. What is a little bit different is that we also provided the ability to choose the date range. So most of the dashboards out there, they just give you the current situation. Just to make it a bit different, we provided the ability to switch to different days. And we source this information either from official APIs provided by government agencies. For example, in Qatar, there is an API where we can source all this information. And this data that we collect daily, it gets fed to the prediction model that Dr. Ahmed has explained. And basically, our daily cases, you can see here, you can see the actual, and you can also see the forecasted values, either for the next 14 days or next 7 days or the next 30 days. So these are the ranges that we have provided. So the users, they could look at the current situation, and they, after this dashed line, it shows the prediction for a particular country. So you choose the country, and then you choose the prediction range, and the graph will change accordingly. Now, we also did summaries. Again, in here, not much different compared to other dashboards out there. But in here, we just give a summary and comparison between the different GCC countries using both a heat map and this bubble graph. Additionally, we give other graphs just as a comparison. This is just for completeness. So if a user comes here, they can get a picture of the current situation, and they can do some prediction of future situation. Now, in terms of the Whatif analysis dashboard, so what you see on the left are the possible lockdown measures and the levels, the typical levels of these lockdown measures. So the user can select the level of the lockdown measure and then apply these hypothetical scenarios. And these parameters get fed to the prediction model that Dr. Ahmed has explained, and then it outputs the predictions for the next, I think 7 days or 14 days. I think it's parameterized, if I recall. So that's basically what the dashboard is all about. It's just providing this in a user-friendly way, hiding all the complexities, so the end user can get just the predicted cases for the future or predicted cases given some lockdown, like easing or either easing or increasing the restrictions. Okay, so this work has resulted in this practical dashboard that I demonstrated, and in these 2 publications that are currently under review. So basically, in conclusion, the deep learning models that we have developed, while considering the socio-demographic characteristics as well as the health sector indicators and the lockdown measures, including all these factors into the trained prediction model, has yielded a prediction model that provide more accurate predictions compared to related work. And also the additional benefit is the model is also capable of doing the prediction given some different scenarios of easing or further restricting the lockdown measures. So as future work, like we can further explore predicting other indicators. For example, now our prediction model is mainly focused on the daily cases and the cumulative cases. It could be extended to predict other cases, such as the number of deaths or ICU units needed or other indicators. It can also be extended, the model and the dashboard could be extended for regional and global predictions. So currently we mainly focused on Qatar and GCC, but the model can be easily to other countries and other regions. So with this, thank you very much. If you have any questions, you are welcome to post them and then we'll try to address them.
Okay, thank you so much, Dr. Abdelkarim and Dr. Ahmed. So with this, we open the Q&A session. So as I mentioned before, you can address your questions either to Dr. Abdelkarim or to Dr. Ahmed. Maybe I will start with a question first. I was wondering that, so you have, of course, you have your modeling work and then you have the output, as you mentioned, because obviously people want to have something tangible. They want to have a tangible outcome, and you developed this dashboard and this web-based platform. I was wondering, in your models and in your platform, do you take into account the size of the population? Because of course you have all your nice prediction models with the number of cumulative cases and what the effect will be of the lockdown and so on. So do you also take into account, for example, the population size, which might be very different from Qatar to any of those other countries that might share similar, demographic, socioeconomic features and so on? So I'm not sure who to address it to, so please feel free.
Yeah, so actually in our cluster analysis where we grouped countries sharing similar properties, we took into account the density of the population, not the population itself, but the density of population. So kind of reflecting the population itself. Okay,
great, thank you. And then I can ask it maybe to you, Dr. Ahmed, because in the introduction, it was also mentioned that when you look at the demographic features of the populations, you also look at age groups.
Yeah.
And you did mention certain predetermined age groups. Can you maybe elaborate a little bit why you chose these cutoffs and ages?
Actually, we looked around the state of art and what could affect the the increase or decrease number of COVID-19 cases. And it turns out that there are several research work that use that particular segmentation of age groups. So 0 to 4, 5 to 9, and then 10 to 14, and by 4 or 5 years up to, I think the last category is above 65 years old. So, yeah.
Okay, and related to this, how do you, because again, you mentioned that if you look at the model with the lockdown policies, that you notice that schools and what was it, public transport? No, open borders, yes.
Yeah.
That those were the main factors where you could actually really see an exponential growth in the cases.
Indeed.
So looking at, again, the age groups you just mentioned, does this have anything to do with it? Or what are the common factors between those two parameters?
Actually, in the lockdown measure, we did not basically reflect the age group in the what-if analysis. We focused essentially on the policy itself, the policy each country has adopted, like in terms, and we focus on two characteristics, how fast and how efficient. So how fast is basically the difference in days, and how efficient is the R0 score. And I believe that R0 score itself kind of tell us about the growth or the evolution of, or the spread of the virus itself in the population. So maybe the information about the age group or the information about the population itself kind of is behind the scene and reflected in the R0 score. So.
Yeah, I wanted to add one more thing, like for the socio-demographic metrics that we have considered, such as the age groups, such as the health indicators, such as the percentage of smokers, the number of doctors per 1,000 population, and other indicators. We first use them to increase the data, the input data that will be fed to the prediction models. So it is well established that these, especially deep learning models, the more data they have, there is more likelihood to produce better prediction models. So to increase the data size in a meaningful way, we use these indicators to first group countries that share similar characteristics, so we can, in a meaningful way, get their data and feed it to the prediction model. So instead of, for example, instead of predicting Qatar cases just based on Qatar numbers, why not expand these input data to similar countries? Now, these similar countries, how do we establish these similar countries? By looking at this socio-demographic factors and the health indicator factors. So this helps us to basically meet this prerequisite of providing enough data to allow the model to learn patterns and to allow the model to build a better prediction and yield a better accurate prediction.
Okay,
so
that makes
that's
sense.
how these factors are included in the study.
Yeah, okay. And then I have a question regarding the model for the forecasting of COVID-19 cases. So you mentioned that you have used this bidirectional STM model. Yes, and that this allowed you to basically look at past versus future and future versus past. And that using this approach helped you to actually improve the performance of the model. So the question is this kind of modeling also used in other prediction algorithms or models somewhere else in the world? And has this been used for a similar setting, like infectious diseases?
Actually, for LSTM, as I said, it's most suited for sequential data, when you have data that is sequentially and time-stamped, for example. So LSTM, by design, is most suited to this kind of forecasting or this kind of problems. For example, similar to LSTM, ARIMA model itself is suited for time series forecasting. LSTM also the same thing. So in our literature review, most of the contributions used, we found that most of the contributions and available publication used indeed, most of them ARIMA or a variety of ARIMA, a model that is built on top of ARIMA, and also LSTM. LSTM has been like, it's kind of intuitive for people who are familiar with machine learning and deep learning to apply LSTM to this kind of problems when you have sequential data like the daily COVID-19 cases. And so our contribution here is to move it to the next level, which is using bidirectional LSTM. And as Dr. Abdelkarim highlighted, data from several countries. So as far as I know, actually to answer your question, as far as I know, indeed, LSTM essentially has been widely used for infectious disease. And for people who contributed to the same problem that we have addressed, indeed, most of the publications, we found that they targeted journals related to infectious disease and this kind of journals and this kinds of topic. So.
Yeah, I just wanted to add one more aspect, is that these techniques are widely used, widely established in many domains. What is novel is how you use them, what data you feed to them, how you configure them. That's the novel aspect. But the general structure and the general inner working is well understood and is well established. So the novelty is how you design the model, what you feed it. So in our case, like even us as individuals, we learn better through accumulation of experience. The more experiences we get exposed to, the better we become, the more we advance in our career, in life in general. Similarly, these models, the more you give them different data covering different scenarios, the better they learn. So what is a novel aspect in our work? So again, instead of predicting Qatar cases based just on Qatar cases and based just on the countermeasures or lockdown measures taken by Qatar government, this would be very restricted because it's a small set of decisions and small set of scenarios. So we needed to expand the input data. In a meaningful way. We cannot input these lockdown measures from around the globe because they are so different, and feeding them all together in the model will just be confused like us and not be able to do any meaningful predictions. So we first try to group countries that have similar lockdown measures. What do we mean by similar? Similarity here is measured by two indicators: how fast they were in taking such measures and how effective those measures were. So the countries that have similar kind of response, we put them, we cluster them together, and then the data related to their cases and the data related to their lockdown measures are fed to the model to learn from these data that is collected. So this way, the model is exposed to more cases and with the hope that it will yield better predictions. So that is basically the novel aspect of it. But in terms of applying the techniques, everybody apply kind of similar techniques. But it is more the way you design your model and the more the way you feed the data to your model. That's what makes difference to the results.
Yeah, that's actually great that you explained this, because this brings me to my next question. Because as you explained, yes, focusing the model on only Qatar would be probably too strict because, again, Qatar is quite small relatively to other countries in the world. But if we think about larger countries, would it be better or would it be in a way more accurate to design the models like more customized for each country rather than having them grouped in those clusters? And the reason why I'm asking is because you mentioned that, yes, the lockdown measures are quite different between countries. So that's why, yeah, this question came in as well.
So I can say that for the our approach is kind of applicable to almost all countries around the world. So once you conduct your cluster analysis and you want to zoom in into specific country, let's say a large country such as the United States, you will focus on the cluster where the United States itself is located. So you'll certainly find the USA member of a cluster with countries that have similar properties to the United States itself. So probably, for example, for the first research track, we found that Qatar has similar properties to its neighbor country, UAE, Oman, etc., etc. So for the United States, for example, we may end up, we did not investigate this, but you may end up, let's say, with, for example, Russia or neighbor countries such as Canada, although maybe it's kind of different. But you will end up eventually with countries similar to USA in terms of the data you have used to apply the cluster analysis. Once you zoom in into a specific country, then you can train your model to forecast whatever application you want.
Yes, exactly.
But more importantly, these countries are clustered based on how effective they were. For example, maybe US will be more with Brazil, for example, because they kind of took similar mindset in dealing with the pandemic. So most likely the impact on the numbers and the impact on the future cases is based on the past behavior, how government how serious they took the pandemic and how effective, how quick they were in responding, how effective the measures were. So it makes a lot more sense to basically try to learn the impact of lockdown measures on the number of cases for countries that have similarity. This will yield much more meaningful predictions. And that's what our results kind of show. It still needs further validation, but at least for the cluster that we focused on, which is Qatar cluster, it yielded much better results than just considering, let's say, the number of cases.
Yes, it's a great model, and I mean, you have a nice web-based interface. So now the question is, what's next? Are you thinking of, let's say, making an app, as everyone is doing nowadays? Because there are COVID-19 apps out there. So is this something you have in the pipeline or you're thinking about?
Yeah, our challenge, as you know, in the academic is usually like you have a project, we work on it, and then so many other things come in, and then we just move on. So hopefully we'll get some helping hands. You know, we have very, very busy schedule. So some helping hands from maybe master students to move this forward. But for us, what is realistically can be done, we just wanted to put whatever we have produced in some stable environment, make sure it is always fed with the latest data that is collected daily, retrain the model, and republish it to the dashboard. So at least what we have produced is still meaningful over time. Now, moving it forward will depend on getting some further funding or some further helping hand. Just by ourselves, we hope we can just sustain it, sustain a stable deployment of what we have produced, and hopefully seek some further funding and student involvement to move it forward.
Yes, I hope so for you, because that would be great if you can develop this further.
Yes.
I just got one more question. Is there a specific lockdown policy that you have seen during your testing that resulted in the greatest reduction of the number of cases? Is there like a specific one you can pinpoint at?
Actually, we did not explicitly investigate such problem. That could be indeed a great research, a third research track to add to our project. But we mainly essentially focused on the what if analysis in terms of policy. So we wanted to kind of say, what if a specific scenario in terms of lockdown you want to establish? Okay, feed it to the model and investigate the output of what the model would forecast. But to pinpoint into a specific lockdown policy that usually resulted in reduction of number of cases, we did not investigate this.
Okay, something to do next.
Evaluation, I think. Sorry, I think the evaluation indicated more like easing the travel restrictions. Our model indicated that is the highest factor that would contribute to comeback or to contribute to an increased number of cases, according to our model.
Yeah, well, thank you for mentioning this, because this was my last question or remark. What does your model predict for us for the next coming 1 to 2 months? Because as you know, people have been locked up for a long time. People want to travel at the end of the year. So what does your model predict?
Unfortunately, as I just mentioned, it just predicts the bad news, like opening, like let's say, public transport, even easing restrictions on schools. The model still predict numbers that are similar to the actual. But surprisingly, opening the borders, especially without like quarantine or opening the borders, that's what upset our model. It's just skyrocket. Yeah.
You'll have like direct exponential growth in number of cases within few days. So,
yeah, I was afraid that you would answer in this way. All right. I think with this, we're at the end of our webinar today. So thank you so much, both Dr. Abdelkarim, Dr. Ahmed, for sharing your data, your modeling in what was a very short time, because again, you only had 3 months to develop and to train this model. So that's a huge achievement. And you even have something tangible as an outcome. You have your platform ready. So you did a great job, I believe. And I hope you will be able to get some more funding or hands to move this forward. So yes, and as a last note, as I mentioned, we are all hoping to be able to, go out, meet with family again, with friends. But yeah, we have to be careful still. We don't want your prediction model to skyrocket, so we will have to stay home for a little while.
Yes.
So yes, so thank you again so much.
Also, just to thank the 2 students who contributed also to this research findings, Hussein Ali and Abdul Mun'am, both usually contributed to this research outcome and practical outcome.
Yes, thank you very much.
Great.
For reminding us, yes.
Yes, that's great. Okay, so thank you so much, both of you, for being on our seminar today as our guest speakers. And then I would just like to remind all the attendees that the session has been recorded. So if you want to have another go at it at a later time point, you can, or if you want to share with someone who was not able to attend, you will be able to do that, because there will be a link on the HBKU YouTube channel. And at the end, when we leave this session, there will be a pop-up window to give some feedback. We would appreciate it if all attendees can give us some feedback for the session today. So with this, I would like to wish you all a very good day. And thank you so much again for joining us today.
Thank you.
Okay, thank you very much. Thank you.
Thank you.
Thank you.